Okay, welcome everybody to our webinar today on new modalities for 3D virtual screening of ultra-large chemical spaces. My name's Mark Mackey. I'm the Chief Scientific Officer for Crescent, and with me today I have Dmitry Radchenko, who's the Head of Parallel Chemistry at Enamine. So we're going to be presenting some exciting new work that we've done jointly on doing sort of 3D virtual screening in very large chemistry spaces and how that can work and how you can get good results out of it. So we shall kick off with Dmitro's presentation. So Dmitry started off with a sort of promising career when he got a silver medal at the 34th International Chemistry Olympiad back in 2002. He then stayed with a chemistry career and ended up doing a PhD in organic chemistry at the Kiev National Taras Shevchenko's University with Igor Komarov, and then did a postdoc at the Karlsruhe Institute of Technology in Germany in Enamine group. Dmitry's worked with Enamine since 2007, so he's been there for quite a long time now, starting off as a humble organic chemist, and has worked his way up to be head of parallel chemistry, a position he was appointed to back in 2018. So as head of parallel chemistry, Dmitry has various responsibilities and interests, including the enlargement of the Enamine REAL Space database, the synthesis of large screening libraries using parallel chemistry, the supervision of pre-plated libraries of screening compounds, and development of in-house tools to work with chemical data. So to tell us more about the Enamine REAL Space collection, I'll pass over to Dmitry.
Hello everyone, and thank you, Mark, for the kind introduction. So today I would like to give you a short overview of what real compound is and what is the idea behind those compounds, and most importantly, how you can access those compounds and use it in your work. And I would start with the definition of real. So real is an acronym of readily accessible. And what's more important here is that the idea behind those compounds is just like that. So the compound should be accessible with high success rate. And that idea was actually straight from the beginning in our head. And to do so, to maximize this feasibility to synthesize those compounds, we decided to use only stock available building block, which we have here at Enamine. And we decided to combine those building blocks using already established reaction which we have in parallel chemistry department, and in such a way, by combining those two entities, we enumerated the huge, really enormous virtual space of compounds which can be readily synthesized from available at-hand building blocks. And so the first idea, and probably the major feature of real compounds, is that they are readily synthetically available. Yes, so here on the slide you can see the chart which shows a number of syntheses which we perform over the last 4 years by months. And as you can see, we typically do a lot of synthesis from 20,000 to 45,000 per month. And so by doing such a huge number of experiments, we obtained a lot of information about the reactivity of our building blocks, about the reactions. We actually synthesized and now have in stock about 4 million of screening compounds. I mean, there's a catalog collection which we have here in Kiev, and most of them we obtained by parallel chemistry department using the real as a source of the structures. With all this statistics about the reactions, we are able to achieve a really great success rate for the synthesis, about 80% for average selection from real collection. Yeah, so and to go a little bit deep more into the validation, how we do the validation of the reagents and reactions. So I have here an example of one reaction which we actually added recently, a few months ago, to the real. This is a 3-component reaction, which is basically sulfamidation and gel arylation reaction using 2 different set of amines. And as you can see, the size of the reaction is really huge. It contains billions of combinations. And to validate, to test whether we can do the reaction and whether our workflow and employees in the labs, our purification, the whole workflow can deal with that. We actually did about 2,000 syntheses, test syntheses. And at the end, we achieved the great results, and the average success rate for this reaction is more than 80%. And now these reactions, I mean the compounds which can be obtained by those reactions, is in real at the moment. And here on the right is an example of 2 sulfur chlorides which can be used, which were tested for these reaction. And this on the left showed only a low success rate of 36%, and it was discarded from the reaction. And this one on the right showed good success rate of almost 80%, and it was included and now a part of the reaction. Okay, so now let's move next, and I should tell you a few words about our building blocks, because without building blocks, the real compound just won't be there. We have, I mean, Enamine have a huge collection of stock available building blocks, and because of that, we can enjoy different reactions and combine them in a way to obtain real compounds. As you can see, we have a lot of carboxylic acids and amines, primary and secondary, and that's one of the reasons why we have so much amides, because we just have a lot of reagents, but reaction also is quite successful. But we also have a lot of other chemical classes, like aryl halides for arylation, alkyl halides for alkylation, and so on, many of them. You can see the numbers of distribution of the building blocks by chemical class, which we have in stock at the moment. Yeah, and talking about the building blocks, it's not that the number of building blocks is the same in stock. We actually synthesize a lot of new building blocks each year, and here on the chart you can see this blue bars is a number, and this y-axis on the left here is a number of building blocks, new building blocks without resynthesis. New building blocks produced each year by our building block department, and so it's about 25,000 new building blocks per year, which gives us about 2,000 new building blocks per month. And a part of our work at Parallel Chemistry Department, my work, is to add those new building blocks to the set of reagent used for real library. In that way to increase the size of real compounds. And here on the right, and also the red line here, is the cumulative sum, the total sum of new building blocks which we have in stock. And now it's about 300,000. Okay, so now I would like to tell you about a few options how you can access those compounds, real compounds. First of all, I should say that the whole real space of compounds is really huge. It's about, our estimation is about 3 trillion of the molecules. So it's really, really huge. And for the client, we have prepared a subset of it. And the first subset which I would like to tell you about is a real space. And we suggest real space as a fragment-based, which means non-enumerated subset of the whole real virtual space, and the size of the subset is 48 billions of combinations, but just 40 billions of different unique structures. First of all, I should say probably about the fragment-based nature of real space. Fragment-based means that we do not have the smiles for the final molecules in this file. We only have these parts of synthons or reagents and the rules how we can combine them. And this allows us to search more compounds, but you need a dedicated software. You can use available on the market or run your own software to search this space. So it's more tricky to work with that. I told that it's a subset of the whole Enamine available chemical real space, and to select it, we used some smart filtering by reactions and by reagents. And the idea behind this filtering was to keep the reaction. I mean, we have really big reaction and a small reaction, and so what we try to achieve is to save those small reactions so that are available in the real space, and cut off some big reaction to take just a part of that. Because of the fragment nature, the real space is only 50 megabytes in size, so you can actually work with that if you have a dedicated software, even on a laptop. But it depends what you are going to do with it. So in real space, there are about 80% of S-real compounds and 92% of M-real compounds. S-real is less expensive. Let's say it's more affordable. And the whole file, as an example, you can download it from our friends from BioSolve IT. This is a company which we have established collaboration with, and we actually created together with them the first version of the space back in 2018. And I forget to mention here on the right, there is a physicochemical distribution of the molecules by molar weight and by log P within this real space. So these are billions. Okay, so now let's move to another product, which is real database. First of all, real database is a subset of the real space. So in the past, it was time when we actually had these two spaces which have intersection, but where not every compound from real database was in real space and vice versa. From this year, we decided to follow the rule that real database should be a part of real space. What's important to note about real database is that it is an enumerated file. So this is basically a text file which you can download, and in this text file, every string is one molecule. So there is a smiles in the XML format, and then catalog ID and batch of calculated parameters. And you have like 6.8 billions of the lines in this file. Yeah, so you can download this file from our website, but also you can have the link from FTP if you contact our sales managers. So the size of the real database is smaller than real space, and to filter the molecules, we applied physical-chemical criteria. So we, and you can see here on the right, the profile of the molecules is more attractive than found in real space. We also filtered out reactive groups. We filtered out undefined steroid centers, multiple undefined steroid centers. And for high molar weight compounds, we also just pick the compounds by random sampling. Because this file have all enumerated compounds in it, it requires about 160 gigabytes of disk space, and also it may be hard to work with that. But you don't require any special software to do so. Another great thing about real database is that we try to keep a number of S-real cheaper compounds in it as much high as we can, and it's 30% of S-real compound here. Yeah, so this is probably all from my side, what I would like to tell today. If you have any questions, feel free to ask. Yeah, thank you.
Great, thanks a lot, Dmitry. So we'll move on to the second part of the talk today, which is looking at some of Crescent's software in terms of 3D virtual screening and how we're applying that to the sort of ultra-large chemical spaces that Dmitry has just talked about. So for those of you who aren't familiar with Crescent, our fundamental idea is that if you want to compare molecules and see whether they're similar or not, you should be doing that comparison in terms of shape and electrostatics, because that's what the protein cares about. Proteins don't really care about atoms as such. They care about if molecule A and molecule B have the same shape and more or less the same pattern of electrostatics and donors and acceptors, then if one of those binds to a protein, the other molecule should as well. We developed a technology to describe both the shape and electrostatics of a molecule and compute a similarity score between them. So given that, we can compute an electrostatic score. In this case, for these two molecules, we've got an electrostatic score of 0.66 on a scale of 0 to 1 and a shape score of 0.98. And we combine those into a combined sort of average shape and electrostatic score. And our algorithm allows us to align molecules together and then to calculate this score. And there's a lot of things that our software does downstream of this. The important one for today's seminar is the fact that we can use the score for virtual screening. We can take a query molecule in 3D, and then we can look in a database of other molecules and say, okay, so let's score my query molecule against all of the molecules in the database, compute our similarity score, and then the ones that have a high similarity are much more likely to be active than the ones that have a low similarity. So it gives us a way to filter the good stuff out of the back. Okay, and just pointing out, obviously, we get a pose out of this as well, and there's a lot of other really fascinating things that we can do with the pose as well as the score. And if you're interested, there's many more details on our website about the other things we can do with that. So our traditional virtual screening technology is called Blaze, and it's designed to manage the entire virtual screening protocol for you. So it's a web-based system, uses a CPU or GPU cluster on the back end, and you can upload your query molecule and it will happily go hunting through a wide variety of molecules in its database and pull out the ones that it thinks are most similar to your query. We've been using Blaze for a number of years now. So as a sort of quick case study of a use, this is a project that we did a number of years ago with a biotech in the US. So they're an agricultural chemistry company, and so they came to us for some help. They had a bunch of compounds with activity data in 3 assays, and this activity data, because it's an agrichem company, was along the lines of some of them the plants died, and some of the compounds the plants didn't die. There's no Ki value, there's no enzymatic assay. It was a purely phenotypic assay with a sort of a fairly binary readout. So based on that, our Crescent Discovery CRO scientists were able to work out what a bioactive conformation hypothesis, so in other words, work out what shape these molecules were likely to be in when they were interacting with whichever protein target they're interacting with, because as I said, it was a phenotypic assay, so we didn't even know which protein these compounds were inhibiting, much less what the binding site looked like. We ran Blaze on a number of search queries coming out of that, and the customer in this case purchased about 500 odd molecules and ended up with a 4% hit rate overall, including a number of compounds in different chemotypes. And after a very small amount of medicinal chemistry work, one of those compounds actually went to be launched on the market a few years ago as tioxazofen. So this compound is on the market and was directly discovered out of a Blaze screen that we did in collaboration with this company Divergence, who were later purchased by Monsanto. So we've run lots and lots of Blaze screens over the years in our services division because as well as providing the software, we are also a computational chemistry services provider. And we've done hundreds of virtual screening projects years, and there's a number of publications here if you're interested to have a look at those later, giving some details of some of our successes. Okay, so Blaze works very well, and it is known to be a really good way of finding compounds that are active and that are also, because we're screening in 3D, it's very good at finding compounds that are structurally very dissimilar to the query molecule. So unlike things like fingerprint searches or things like that, Blaze will happily find you molecules that, at least for the chemist's eye, you can look at these molecules at the bottom and say, they have very, very little or nothing in common with the molecule we were searching with, but these compounds are all active against the same protein that this compound was active. And it's reasonably fast. So in terms of sort of running searches against commercially available off-the-shelf molecules, Blaze is perfectly good enough. However, there really becomes an issue if we wanted to apply Blaze directly to the sorts of large databases that Dimitro was talking about earlier. So Blaze will quite happily search through 50 million molecules. Both we and our customers regularly do that. But if you're now looking at the the Enamine REAL collection, you're looking at perhaps 50 billion molecules being available there. That's 1,000 times larger. And if you just take the sort of brute force approach that Blaze does, where we simply conformationally enumerate all of the molecules and then search all of those conformations, you're looking at petabytes of disk space, thousands of CPU years to build the database, and an extremely large computational cost in terms of searching the database in a brute force manner. So you can take some shortcuts here by doing things like skimping out and only calculating a few conformations, but then you're still spending an awful lot of CPU time to perform a search in a half-baked manner that's not going to give you results that are as good as what you'd want. So we really were looking for a better way of doing this. So we were asked by a partner of ours, a big pharma company, Bayer, and they had Blaze. They really liked the results from Blaze, but they wanted to know, could they sort of develop a technique that was like Blaze, but could be used on these data sets that are orders of magnitude larger than Blaze can cope with out of the box. Okay, so again, just to give you an idea of the size of real spaces, so we're looking at tens of billions for Enamine compound. Certainly for some big pharma in-house sort of virtual spaces, they're orders of magnitude larger than that. And you can see that even if you wanted to throw lots and lots of money at the problem, once you start getting to these really large virtual spaces, it just becomes completely computationally infeasible to do things in a virtual, in a sort of exhaustive enumeration brute force way. So how are we going to solve this problem? So in collaboration with Bayer, we came up with a new algorithm that we've called Ignite. And the idea is to take advantage of the fact that these large collections of compounds aren't collections of singletons. It's not 50 billion molecules, none of which look like each other. Actually, that large chemistry space consists of a large number of smaller library spaces. Okay, so rather than looking at them as being a whole bunch of completely disparate molecules, if we can do some intelligent calculations at the synthon level, we can cut down the space to the point where we can search the most interesting parts of that library space and possibly not bother searching the synthons that are unlikely to produce anything that looks like a query molecule in terms of shape or electrostatics. So if we imagine we have a relatively simple library here, sort of two-component library. We've got a couple of synthons. We're going to couple those together to form a library of triazoles, for example. Okay, we've got thousands of these. We've got thousands of these. We've got millions of these possibly to search through. Can we do that search faster than enumerating millions of molecules, confirmation hunting millions of molecules, and then running our search? So the obvious thing to do is to say, well, okay, let's have a look at the synthons and see if either of these look like the query molecule. But there's an issue there in that this synthon is an amidine and this synthon is a nitrile. And of course, our final molecule doesn't have an amidine group and it doesn't have a nitrile group. And so if we simply score these in terms of shape and electrostatics, we can end up getting the wrong answers because it may decide that a particular reagent looks quite like part of our query molecule, but part of that similarity is because of the amidine. And of course, the amidine's not going to be there in the product. So the first stage of our strategy is to convert all of our synthons into what we call a minimum product-like molecule. So this is done specifically for each library. So in this case, we would prepare all of the reagents for this triazole library so that all of our R1 groups get turned into a minimum product-like molecule where the R1 bit here is connected to a 1,2,4 triazole. And similarly for all of our R2 groups, we convert all of the nitriles here again to a 1,2,4 triazole. What we can then do is run a sort of Blaze-like search of these minimum product-like molecules against our query molecule to see which R1 groups here and which R2 groups here end up making the resulting partial molecule look similar to our query molecule. And obviously with some R1 groups here and some R2 groups here, these are going to fit quite nicely against part of our query molecule. With other groups, actually it's going to be hard to find any way in which those look similar. So if there's an R2 group where, having put the R2 group on here, this fragment just doesn't look like any part of the query molecule, then in essence, it doesn't really matter what R1 group we put on this side, that's never going to be any use. And as a result, we can, in essence, scrub out an entire row of our combinatorial chemistry matrix. And there's a whole 1,000 molecules there that we just don't need to look at because we know that that particular R group is never going to produce anything that's that interesting. So we do this initial pre-screen in fragment space in order to cut down the number of synthons to the ones that we think are of primary interest. And we do that on both ends. So we'll keep all of the R1s that look interesting and test those with every possible R2 at the other position. And we'll also just look at the R2s that look interesting and test those with all possible R1s. So all of the R1s and all of the R2s do get a look in, but they only get a look in cases where their partner has already been decided to be at least of minimal interest in terms of its shape and electrostatic properties. So that obviously allows us to cut down the search space significantly. And at the end of the day, we can then sort of enumerate on the other end and perform a scoring according to our shape and electrostatic score. And we end up with a score that's exactly the same as the score you would have got for this final product molecule if you'd used Blaze. But rather than pre-computing conformer spaces and searching on as we go, what we've done is we've only bothered creating product molecules in parts of the chemistry space that appear to be interesting. And this obviously massively reduces the computer time that's needed. Okay, so in essence, we're taking shortcuts here. We're not going to search the entire library space. We're just going to search a subset of the library space. But we think we've got a quite intelligent and efficient algorithm to really focus in on those parts of the library space which really are of interest and that are going to produce molecules that look in terms of a shape and electrostatic version of look like the molecule that we're searching with. Okay, there's a number of sort of technical challenges in doing this. For the 1,2,4 triazole example, this is reasonably straightforward, but for some chemistries, this turns out to be quite complicated. So we started off with a sort of simpler example. So as I mentioned, we were working with our partners at Bayer Pharma. They wanted to search their own internal small combinatorial library space, which is called base space. And this had sort of roughly 57 two-component reactions that were going into it. And so we sort of hand synthesized the sets of rules for each of those 57 reactions in terms of how we pre-prepare the reagents to form those minimal product-like molecules, and then how we form the joining rules to convert those minimum product-like molecules into the final molecules that we're going to do the final score against. And there's a whole heap of complicated cheminformatics you need to get right in terms of regioisomer formation, in terms of stereochemistry and so on, but we were able to solve all of those problems as we went on. We then started working with our partners at Enamine, and this started to get a little bit more complicated simply because they have a much wider variety of chemistries available to them than Bayer did. So there's an awful lot more synthesis protocols that we needed to perform. And as a result, sort of doing that sort of handcrafted preparation of library space, was just going to be too much work. So instead, we've developed an algorithm which, given the sort of description of the reaction that we're going to undertake, turning the two synthons into the final product, we can automatically detect what the minimum product-like molecule motif is going to be and automatically stitch that onto the molecule. So this greatly eased the pain of getting a new library space up and running, that nearly all of the library spaces that we're looking at can be handled by this automated algorithm. And it's only in a very small minority of cases do you actually need a cheminformatician to look at this and slightly tweak the automated algorithm in order to produce molecules that are going to perform well in that initial pre-screen in shape and electrostatics. So we've done a bunch of benchmarks just against Blaze by, in essence, defining relatively small library spaces where we can compare the results we would get from Ignite to the results that we get from running Blaze, from actually fully enumerating the molecules and testing it. And Ignite performs very well. It's highly enriched with the molecules that would turn up in the top hits of Blaze. So you are getting all of the molecules that you would find from a Blaze search, but obviously disregarding a large portion of the chemistry space. And we get an excellent speed up relative to Blaze. So these numbers here are an underestimate due to the way Ignite works with cutting out parts of the chemistry space. The larger your library space, the more efficient that pruning can be. So even on a relatively small library space, we're getting about a 20-fold speed up compared to what we get by doing the brute force calculation in Blaze. And as you move to larger library sizes, that speed up turns into the hundreds or thousands. So it's noticeably faster running Ignite on a large space than it is enumerating the molecules and running our full 3D and shape similarity calculations there. So looking at a subset of the Enamine REAL Space that's been sort of pre-filtered. So this is sort of data from inside Bayer. So they're searching about 3 billion molecules on this sort of pre-filtered database, and it takes them just a few hours on a relatively modest CPU cluster. So this is a calculation that's easily runnable if you have even a modest in-house cluster, or it's a calculation that you could run, for instance, on the cloud for a very, very modest outlay in terms of total compute cost. You're talking tens or at most low hundreds of dollars, not thousands or hundreds of thousands of dollars. That you'd need for the brute force enumeration and search. So our partners at Bayer have been using this quite intensively. So this is sort of an example they've shared with us, and unfortunately the target is still embargoed, so I can't give details on that. But it was a project they'd had running for a while. They had some good compounds, but they were looking to try and find some new chemical matter, so some new lead series to work on, the backup series. And so they did that in two ways. They ran our bioisosteer finding tool called Spark, which is an excellent way of finding a way into new parts of chemistry space. And Spark did indeed manage to suggest a number of interesting new cores. And based on that, they made 30 of the Spark suggestions, and they found a number of new cores, the best of which was a 9 nanomolar compound that did have some of the same R groups, but did have a significantly new core and got them into a new region of chemistry space. So that was interesting. But then the follow-up experiment they did was to say, okay, well, let's now look for something that's completely new. As I mentioned, Spark looks at bioisosteers, so it's changing part of the molecule, in this place the core, while keeping the rest of the molecule the same. But they wanted to see, was there anything nice that was sort of lurking in chemistry space where, in essence, you're throwing the whole molecule away and looking for something completely new. So they ran an Ignite search in this case, starting from one of this Spark molecule here. They ended up synthesizing just 10 compounds from their library space that was suggested by Ignite, and one of those 10 was a completely new class of molecules, structurally unrelated, and again, with a double-digit nanomolar activity, which is an excellent starting point for further optimization. Okay, so this shows the power of Ignite. So in this case, their library space was sufficiently large that the brute force calculation would have been a very hard slog. But Ignite managed to speed that up. They could run this search in a couple of hours, and pretty rapidly were able to find completely new molecules unrelated to their existing series, but with a high activity and something that you can easily take on and optimize further. So just to give you some visual pictures of the sorts of things we can do. So we applied the algorithm to a known compound, which is a SARS-CoV-2 main protease inhibitor, just to show you the sorts of hits that we provide. And again, at a relatively small amount of CPU, the top ranked suggestion coming out is this molecule here. And you can see that in terms of shape and in terms of electrostatics, the molecule that's being suggested matches this protease inhibitor very nicely. And so it would be a good candidate for synthesis and for testing if you wanted to find a completely new chemical matter unrelated to the molecule we started with. So that's sort of Ignite. So at the moment, Ignite is available as a sort of technology. So we're providing access to Ignite via our services division. And we're also looking for people to work in partnership with us to improve and further validate the method. and it should be coming as a sort of fully fledged software product in the near future for everybody to buy and use on their own, either on their own library spaces or on library spaces such as the ones from our partners at Enamine. So thank you very much for listening to the presentation today, and if you have any questions, then please do stick them in the question part of the box, and either me or Dimitro will be more than happy to answer them for you. Okay, so first question we've had come up is actually for Dimitro. Somebody asked, what's the major factor in the expansion of the real space? So I've sort of paraphrased that as, what's your strategy for making the real space even bigger than it already is?
Yeah, so thank you for the answer, really great. First of all, there are two factors how you can increase the size of any virtual library, not only the real space. The first one is the number of building blocks which you use. So quite naturally, if you have more building blocks in the reactions, the size will grow. And I saw you the slide there showing that we actually synthesize every month a lot of building blocks. And this is one way, and it was the major for real until 2018, I believe. Because after 2018, we decided to more aggressively, let's say, add new reactions to the real. And since then, we added many new three-component reactions, which had a really huge impact on the size of the real. So we experienced like an exponential growth in size. Yeah. So overall, after 2018, the major factor is in new reactions. Yeah.
Okay, thanks, Dimitro. So there's another sort of related question. Actually, there's a couple of questions that I shall combine together, I think. So you mentioned that you do provide this sort of database of sort of synthons and connecting rules. So is it possible for users to, in essence, use those as a reaction scheme in order to look at the space of molecules that are provided as part of the Enamine real space? And can users combine those reactions in a series of reactions to make more complicated products within your space?
Yeah. So yeah, we provide this space. Actually, there are several formats how we can transfer this information about the synthons. So one is what I mentioned to use this dot space file, which is available from Biosolve IT, and use a software to search it. But we can also share the information under the license agreement, of course, about our synthons. And yeah, every user can use this information about reaction, about the synthons, and to combine synthons in a way encoded in the reaction and do some research like you, Mark, showed when you applied it to search for the 3D structure. So something like that can be done with those information, yeah.
Thanks, Dimitro. Okay, so another question, this one for me. So I had a question, does Ignite work for covalent compound virtual screening? So the answer to that is yes. So Blaze and sort of by extension Ignite is a ligand-based virtual screening method. So we're not doing docking, so we're not directly paying attention to the protein. So there's an element where for covalent compounds, you need to think about the warhead that you're going to use. So obviously the constraint there is that you would want your warheads to be aligned. Obviously, if I find a molecule that's got a great sort of electrostatic and shape similarity, but my original molecule is like this with the warhead up here, and the other molecule has great electrostatic and shape similarity, but binds with the warhead down here, that's obviously not going to work. So both Blaze and Ignite have the ability to add constraints. So in this case, what I would do is set up the library space and set up my query molecule with a common warhead. And then using constraints, you can basically enforce it though, so that the warheads have to align with each other. And you're then looking for molecules where the warhead is in the same place, but the rest of the molecule needs to match in terms of shape and electrostatics. And that obviously will end up providing you with molecules that, with luck, should work as covalent inhibitors in the same way that your query molecule, which presumably was a covalent inhibitor, worked. Okay. Other questions we have. Okay, so yeah, so there's a question somebody had about does Ignite work with 3 and 4 component libraries? So at the moment, the technology we have in-house really only works with 2 component libraries. So we are looking at only a subset of the full space, but we have an active research project at the moment on how we can expand the technique to search in 3 or 4 dimensions rather than just in 2-dimensional libraries. So that's looking reasonably promising, but I don't have any sort of results of that yet. So I'd hesitate to say we can do it, but watch this space. Hopefully we can come up with some good news on that front in the near future. Okay, just a reminder, if anybody else has any questions, then please just use the question part of the GoToMeeting chat. Okay, so another question. So this one's for Dimitro. How does the Enamine REAL Space compare to the other commercial chemical spaces?
Well, I'm not a specialist in, say, other commercial spaces. I can tell you what's different, in what aspects Enamine is different from the others. And the first one is, of course, synthesizability. Probably Enamine is most focused on the success rate of the synthesis, but not on the expense on the price of the compounds. I mean, with the parallel chemistry, well, let's say, you can make it almost any compound. It's a matter of budget which you have to make those compounds. And for real compounds, we try to keep the price as low as possible. So the typical price is about $100 to $200 US. And during this budget, we have optimized our reactions and reagents to achieve a high success rate. And this is probably unique, makes a real database unique. And also availability of the building blocks, which we have. I mean, you have a very diverse final molecules, and when you order them, we can start with synthesis straight away. I mean, our stock located maybe 50 meters from me here, so I can go there, took the vial, and start the synthesis straight away. I'm not sure that all other vendors have such possibilities.
Great, thanks, Dimitri. So I think that's covered all of the questions that we've had come in. So I'd just like to finish up by thanking Dimitri for presenting, and thank you, the audience, for coming to see our webinar. I hope it was informative. And obviously, if you have any further questions, either about the Enamine compound collection and the nifty things you can do with it, then obviously, please contact Dimitri. He'd be happy to provide you with more details. Or if you're interested in using Ignite as a way of searching these large virtual library spaces and finding interesting molecules via a 3D search, then obviously your local friendly CRESA representative will be only too happy to help. But apart from that, thank you very much for attending. I hope that was useful, and I hope to see you at another webinar soon. Bye all.
Bye-bye.
Bye-bye.